Okay. So today I would like to start the discussion of the convexity theorem. And well, let me first recall a small thing from what we saw before, and then we state the convexity theorem and start discussing its proof. Probably we do a big part of the proof today, and then maybe finish it next time. So, as usual, we look at Hamiltonian T spaces, and we choose the group to be a torus. So, in Hamiltonian T space, let me make it compact and connected for the purposes of today's lecture. And let's look at the fixed point set for the torus action, right? So these are points on M such that all elements of T map it to themselves, right? So let me recall that this fixed point set is actually a union of smooth submanifolds of M. So it's a disjoint union of Fi's, where Fi's are submanifolds. Yeah, it's very difficult in the morning of M. So since I assume that M is compact, so this will be a finite set. Submanifolds of M. So here is M, and here are sitting those Fi. So they might be just isolated points, or they might be submanifolds. Now, claim. So if you restrict the moment map to Fi, it will be a constant. So we have those fixed point, connected components of the fixed point set, and actually our function mu, our map mu, restricts to constants on Fi. So why is that? Right, so let's consider a vector field on M which is tangent to Fi. In particular, I choose M on Fi, and I say that Vm is sitting in the vectors in the tangent subspace of Fi. So my vector field here is tangent to this Fi. Right. So I would like to compute V of mu at the point M. So I differentiate the function mu with the vector field V, and I compute the value at the point M. But this is a function with values in a vector space in T star. So to characterize it, I would need to compute it on various elements of T. So this would give a complete characterization of this function. So maybe we can rewrite it a little bit. So this is the same as the Lie derivative with respect to V of the function mu psi, and all of it computed at M. Or if, as usual, we apply the Cartan's magic formula, we can say that this is iota of V of D mu psi, and all these computed at M. But this is equal to iota of V iota psi M omega, so that's because this is a Hamiltonian T-space, right? That's just the moment map condition. And this is all computed. This is all computed at M. Right. Now, let me recall that this set, it also have an alternative. It also has an alternative description. So this is the same as points in M where all fundamental vector fields vanish, right? So this is the infinitesimal description, and this is the global description. Now, well, what is this? So this is omega of psi M of M Vm, right? So that's just another writing for this expression. And since the fundamental vector field is 0, so this must be 0. So we see that the vector fields which are tangent to Fi, they kill mu. And since Fi's are connected, this means that mu should be constant on Fi's. Right? Constant since Fi's a connected submanifold. Right. So in particular, this whole story implies that mu of mt inside T star is a finite set, right? So we have a finite number of those connected components of those smooth submanifolds. On each submanifold, on each connected component, mu is just a constant. So each of those submanifolds is just mapped to a point. So we have just a finite number of points as the image of this fixed point set. Right. So now I would like to state one of the versions of the convexity theorem. So it's due to A Bott and Gilman-Sternberg, and these are two independent papers, so which have different proofs, somewhat different proofs. So in fact, for me, in preparing today's lecture, kind of a very long time took a hesitation between the two proofs. So in the end, I think we settled to somewhat updated version of the Gilman-Sternberg proof, but then in the exercises there will be some glimpses of the Atiyah's proof. So, the setup is the same. We have T, a torus, and we consider a compact connected Hamiltonian T-space. So then the following is true. First of all, the image of M is a convex polytope that is an intersection of a finite number of half spaces. And second, mu of M is a convex hull of mu of MT, meaning that this is the, for instance, one can say this is the minimal convex subset which contains mu of MT, or one can say, so this is the set of all convex combinations of points in mu of MT. So we can imagine something like this. So these are points, so these are images of those connected components. So that's mu of MT, and now the convex hull, that's this set. So this will be mu of M. If the yellow points were images of elements of mu of MT. Perhaps a small remark. In this formulation, it's not guaranteed that this so-called polytope is of dimension of T star. It might be that it doesn't have interior points. So maybe some of the half spaces are just opposite. So you have a plane and a half space on one side and a half space on the other side. So then already this intersection will be the hyperplane, right? And then inside you still cut pieces. So dimension mu of M is of course small equal than the dimension of T star, and it kind of, in many cases, of course, it is equal, but it doesn't need to be equal.
Is it the same that the action is ineffective?
Sorry? Yeah, if the action is effective, then the dimension will be the same. Right. So let me start with an example which illustrates the statement. So recall that coadjoint orbits are Hamiltonian G spaces. In particular, we were looking at UN acting on coadjoint orbits which were identified with conjugation classes of Hermitian matrices inside, so that's inside the space of Hermitian matrices. So here there was some canonical symplectic form, the KKS symplectic form, whatever it is, and the moment map was just a map. Let me call this guy Y. So this was just the identity map. Mapping Y to Y. So here it is inside Hn, which is isomorphic to the dual of the Lie algebra of the unitary group. So Maybe now, if you were not that sleepy and I was not that sleepy, we would notice that actually it's a strange example that I'm suggesting to you, because here we stated the theorem for torus actions, and now I start talking to you about Hamiltonian spaces for the action of un, right? However, of course, we know that inside un you can find many tori, and in particular, say there is this diagonal torus which is sitting inside un. Well, it acts. Now the question is, so it's of course it's again a Hamiltonian action since it's a subgroup. The question is, what's the moment map? So here there will be so that let's say T inside un, and for this T would correspond another moment map. Let me call it mu tilde perhaps. So the question is where this moment map would map y, an element of the orbit. Already we know that whatever we write here, it should be in T star, which is in this case isomorphic to Rn. So any ideas of what this might be? So instead of all unitary transformations, we just take the diagonal ones. So what will be? We know the moment map for the full thing. It just takes our Hermitian matrix and it sends it to itself. Right? So there, it's very, very easy. So what could be the moment map which corresponds to the diagonal?
Can we just restrict the original moment map?
Sure. Yes. And what do we get? Yes, we should. Let's restrict the original moment map, and what will be the result, right? There should be an n-dimensional vector. Here was an n by n matrix, and we want an n-dimensional real vector.
So just the elements on the diagonal?
That's right. So if one does it carefully, so one will see that this will be just the diagonal part. So we just throw away all the off-diagonal elements, and we just take in the vector of diagonal elements. So very good. So we would like to know what's the image of mu tilde. So in other words, we take this conjugacy class. So the conjugacy class consists of all the Hermitian matrices with fixed eigenvalues, right? And now you would like to know, you take the diagonal part of such a matrix, and you would like to know what are the possible diagonal paths, right? So this is equal to those 1 and n. For y equal to g x g minus 1. So x is fixed and g is nu. Okay. For simplicity, let's assume that x, we can always choose it to be a diagonal matrix as well. Well, now if you want to use the convexity theorem, we need to decide what is the fixed point set of T. Right, so we take Hermitian matrices within our with fixed eigenvalues, and we say that they commute. They don't move, so these are y's of the form gx g minus 1, such that t y t minus 1 is equal to y for all t and t. So what are they? So you have Hermitian matrices with, so the eigenvalues are fixed, and now you want to know when they don't move if you conjugate them by elements, by diagonal matrices. So what are they? Sorry? Yeah, say it.
I mean, the latest diagonal matrices.
Sure, absolutely. But can it have anything else? Suppose that your matrix has some off-diagonal entries. Then what's going to happen when you conjugate with such things? Right? So the diagonal entries don't change. But all the off-diagonal entries, they are multiplied by the factors of the type exponential I theta I minus theta j. Right? So that's, you multiply by such a matrix on the left, you multiply by its inverse on the right. So all the off-diagonal entries, they would get some non-trivial phase factors. So basically, if you have any off-diagonal entry, then there is no chance it will stay. So we conclude that this is an intersection of OX with the set of diagonal Hermitian matrices, right? So these are diagonal matrices with real entries on the diagonal. Now, OX, these are matrices with fixed eigenvalues. Now, what are the matrices with fixed eigenvalues which are diagonal? Right? There are not that many. So what is this set? We can, right, so if we start with, for instance, with such a matrix X, we can still permute the eigenvalues, right? And that will be the only possibility. So the set of eigenvalues has to be the same. But by permutations, we can actually get any permutations of them. So these are matrices of the type. So we take this set of numbers, those lambdas, and we ask the symmetric group. So I denote it by Sn. I'm not sure what's the notation that you like, Sn or sigma n or whatever. So we apply all the permutations, and we obtain all diagonal matrices with different permutations of lambdas. So that's basically the answer, right? We now know what is OXT. Now, by mu tilde, it's simply mapped to the set of vectors lambda sigma 1, lambda sigma n, sigma n Sn. Yeah, the claim is that, no, mu tilde, not so good, right? Yeah, by mu tilde, right. So, and the image of mu tilde is a convex hull of this set. So let me give maybe a couple of somewhat more concrete examples. Let me choose n equal to 3. So how is going to work? In fact, this is one of the examples where, even though our torus is of dimension 3 and in general of dimension n, the image mu of m will be always of a smaller dimension. So why is that? So we consider the image under this map of this coadjoint orbit of the set of matrices with fixed eigenvalues. And I'm claiming that it can never be of dimension n, this image. At best, it will be of dimension n minus 1. Why? Do you see it? So let me, okay, so it's okay, so for any n, first of all, for any n, notice that trace of gx g minus 1 is equal to a trace of x, right? And equal to the sum of the eigenvalues. And on the other hand, this is equal to the trace of y, and this is equal to the sum from 1 to n of diagonal elements, right? So this means that the image, whatever it is, it lies in this hyperplane, right? So it cannot be away from this hyperplane. So now back to the n equal to 3 example, right? So here is, let me, so let me make two drawings. So that's my space T star isomorphic to R3. And I know that, so this is, let's say, whatever, y11, y22, y33. And I know that actually the images of my coadjoint orbits, they lie in those. So here I draw this section of the positive quadrant by a hyperplane. The sum of coordinates is equal to a constant. So you can imagine that we have such a corner in R3, and there will be a hyperplane going roughly like that, right? So the sum of coordinates is equal to a constant. And that's why maybe it's more convenient to think that we are looking from this point to the corner and do the two-dimensional drawing. So that's the projection of our 3 axes on this plane, right? So these were the axes: y11, y22, y33. So let me choose an example. So now I have to choose my x, right? For different axes, I will have different results in general. So for instance, if I choose x to be 1, 0, 0, 0, right? So there is only one eigenvalue which is equal to 1. All the others are 0, and of course, off diagonal it is 0. So then, what's the image of the points in the fixed point set? So there is this point, right? 1, 0, 0. And then there will be other permutations. I can put this 1 on any of the axes, right? So there will be this guy and that guy, right? And that's all, right? So there are no other, so there are 3 images here. So this means that the image of the corresponding conjugacy class will be a triangle. Right? So this is the image of MT, and that's the image of M. Let me do one more picture. Here, I'm not sure whether the drawing will be completely adequate. So this was x equal 1, 0, 0. Now, what about x equal, for instance, 2, 1, 0? Yeah, let me try to draw it. Here, as I say, I'm not completely sure how adequate my drawing will be. So I think 2 and 1, so it will be somewhere here. So this is my axis 1, this is axis 2, this is axis 3. So I think that's this point. And now there will be 6 images, right? If I'm not mistaken, this will be something like this, roughly. So there will be 6 images, and the corresponding convex hull will be hexagon. For computing those images, right? And the images do look interesting. And usually the fixed point set, especially the fixed point set for the full torus, that's considered to be a relatively simple object in examples, let's say. The whole manifold may be a rather complicated beast. But the fixed point set, well, of course, maybe it's also very complicated. Then, well, bad luck. Then you need to think of further tricks to figure out how it works. But normally, that's a simpler object. And so you see it produces, at least in those cases, some relatively nice and simple results. OK, so now we'll try to advance in the direction of the proof of the convexity theorem. I don't think we've finished the proof today. And I must say, at some point, probably I'll resort to a little bit of cheating. You will see. Or maybe you should catch me. Right. So we want to know how the image of the moment map looks like. And we start with the local considerations. So we want to know how the moment map looks locally, and then we'll know something about the image. So local normal forms. Right. So again, the setup T, x on m omega, mu m to T star. And so we'll do it in 2 steps. First, we consider a kind of easier case, and then we'll try to figure out what happens in the general case. So I'll first take a point of the fixed point set, MT. And I would like to know how these structures, the symplectic structure and the moment map and the action, right? I now have 3 ingredients, how they look like near this point. I would like to build some kind of local normal form for that. So let me recall that the tangent space, actually at any point, is symplectic. But now we have this point is fixed under the T action, and this means that actually the torus naturally acts on the tangent space. And it is easy to see that omega m will be preserved by the torus action. Right? The torus action preserves the 2 form on m, and now we obtain this structure as an infinitesimal structure for m omega. So the T action is naturally induced from the global T action. So omega m is T invariant. Right. Now the Rebus theorem says something like this. So there is a neighborhood U of M inside capital M, and a neighborhood V of 0 in a tangent space, and phi from V omega M to U omega symplectomorphism. So phi star omega is equal to omega M such that phi of 0 is M. Right? So this was the statement of the Derbou's theorem. Now, in addition, we have now a T action, right? So claim you can upgrade the Derbou's theorem such that the T action, such that on top of it phi, so claim upgrade Derbou such that phi is actually a T equivariant map. So it's a symplectomorphism and it's a T equivariant map. Phi of TV is equal to T 5M. Well, we're not going to prove it, but let's just discuss why it is true. So who remembers anything about the proof of the Derbou's theorem? Moser trick, right? So to start with, it uses the identification of. So we start just with some identification of V and U. Using, for instance, we choose a metric and we choose some geodesic rays, right? Before we do Moser, we need to identify some neighborhood of M in the manifold and the neighborhood of the origin in the tangent space. For that, we typically use some kind of geodesic rays. And since T is compact, we can always choose an invariant T-invariant metric. We can average Riemannian metrics. So, and if we choose the metric to be invariant, we can start even before we do Moser, right? Moser corrects an identification between V and U to get a symplectomorphism. But we start with identification which is already T equivariant. After that, you're right, we do Moser. So we just need to control that whatever we do in Moser, it would always correct our equivariant map to an equivariant map. And so one just needs to check it, and it just works. So with the right choices of the initial identification of V and U, and with the right choice of the homotopy, say we need some T equivariant homotopy that we use in the Moser trick, so Derbou will automatically preserve will automatically respect the T action. All right, so so far so good. Now what about the moment maps? Maybe just one small remark that we didn't need before, but it was often mentioned in the exercises. Right. So uniqueness of moment maps. So recall that the moment map satisfies the following condition, right? So the contraction of the two-form with a fundamental vector field is d of mu psi. So suppose you have some other moment map, mu prime. So then what we get from here is d mu prime minus mu psi is 0 for all psi. And this means that d mu prime minus mu is 0. So in our situation, what we have? So we have a structure of a Hamiltonian T-space on U, and we have a structure of a Hamiltonian T-space on V. And this means, so this consideration shows us that if we succeed in computing the moment map on V, then it can only be different by a constant from the moment map of U. So this implies, for our practical purposes, so mu U minus mu V is equal to a constant. All right. So now our plan is as follows. So we'll go back to symplectic vector spaces. We compute the moment map, and we use now this V with omega m, with the induced T action, and with the moment map as a model for what happens for U omega, the T action, and the original moment map mu. So that's the idea. Since we have only 1 minute before the break, maybe let's just have a break and do it in 15 minutes. All right, so let's continue. Let me first repeat the announcement I made in the beginning, maybe for those people who were not there, that next week there will be no class on Thursday. So that's one announcement. But what I forgot to say, I would like to advertise today's colloquium that will be at 4 o'clock in Battelle, because it's very much related to the topic of the course, to the topic of the lecture last week, and to some extent to the topic of the lecture this week. So for those who are interested, I think this will be a nice colloquium, and it's for you. You will recognize many things, maybe almost everything. Yeah. Okay, so let's get back to this story. So we're now discussing this this local model of our space. So near a fixed point, we now model it on the neighborhood of the origin in a vector space, in a tangent space. Our action restricts to the linear action on this vector space. We have a constant two-form. And now maybe, perhaps let me recall something that we discussed once. So how the structure of the linear T actions on vector spaces looks like. So we know that, let me write it in the following way. So Tm admits a decomposition. Let me write it like that. So it's a direct sum of a vector subspace V0 plus the sum of some number of subspaces Vi. And the T action is just a diagonal T action, where here the T action is trivial. It's trivial. And every Vi is two-dimensional, and we can choose an isomorphism with complex numbers, let's say, such that corresponding coordinates will be Zi. And here the T action is like that. So an element of our torus, let's say, is theta 1, theta k, maps zi to zi times an exponential. And here there will be some vector of integers. Zk, which corresponds to each two-dimensional subrepresentation I. Right. So these are they're also called weights. Of the T action. But now there is a question. And yeah, so here the action is trivial. Maybe just one more remark. So remember, like, let me try to fit in a picture somewhere. So here is our Hamiltonian T space. And here is this point M, which belongs to the fixed point set. So recall that in general, the fixed point set consists of connected components. So maybe it is sitting in some connected component Fi of the fixed point set. Then anyone sees the geometric interpretation of this V0? So what is V0? So that's a subspace of the tangent space on which the torus acts trivially. So what's the relation with this picture? So what is this guy?
It's tangent space to it.
Mm-hmm. Yeah, certainly. So that's the tangent space to Fi at M. Right. Right. So, but now there is a question. We have this nice picture for the T action, and we have a symplectic structure on our vector space. The question is whether they are talking to each other. So can we make it more precise? How this symplectic structure looks like with respect to this decomposition. I will make a claim, and you will prove it in solving the first exercise of the next problem set. So this is a statement in symplectic linear algebra. And we'll discuss a little bit why it is true. So I claim that one can choose coordinates in the following way. So as the symplectic structure completely splits. So there are standard symplectic structures on those VIs, and omega 0 is a non-degenerate on V0. So basically, my symplectic vector space TMM together with a T action is a direct sum of the symplectic vector space V0 with a trivial action plus a number of copies of Vi with the standard symplectic structure and the T actions given by these formulas. See, so everything is really completely prescribed. Now, maybe something should worry you in maybe something should be slightly worrisome in this statement. So this, I would say this word choose. So what does it mean, choose? What is it to choose? So there looks like there is not much of a choice. So let's discuss what these choices are. What do I mean by choices? So what do you think? What can one choose here? It looks like I've already chosen everything. Now it's either true or not. However, just like that, maybe it's not quite true. So what are the extra choices which are possible? So there is one very simple choice about those coordinates zi. What can I do with them? Yeah, I can rescale them. So who knows? You know, for instance, here, if I just do it like that, maybe here there are some coefficients, some numerical coefficients, and I can remove them by rescaling. However, more serious things may happen. It may happen that the symplectic form, when we write it with respect to this decomposition, maybe it's not at all, you know, like maybe it doesn't split. So this may also happen. So when can it happen? So what's your feeling, right? Of course, we would need to solve the problem and like prove things, but let's discuss kind of when such things may happen. And just a hint, it depends actually on what those weights are. Right? So you have an action of your torus. You know that omega is invariant under the torus action. So what may happen with the weights so as this formula perhaps doesn't work so nicely? Maybe another way to put the same question. So is this decomposition, what do you think? Is this decomposition really unique? I said it exists. But what do you think? If it exists, would it be necessarily unique?
Well, there's two representations with the same weight.
That's right. So that's the problem. If the representation, so it's relatively easy to see. Let's assume to start with that all the weights are distinct. So if all the weights are distinct, then it's relatively easy to see that you won't be able to mix, like up to, let's say, maybe the weight and minus weight. So then we should consider as being in a pair. But if weights are distinct and not equal to minus any other weight, then it's basically easy to see that the form has to be like that, possibly with some scalar multiple here. Because otherwise it just can't be invariant. Now, if there are the weights which are the same, so then in principle here you have a choice in the decomposition. And then the form is also not necessarily of that particular, so this particular expression, which is easier, is not necessarily the expression for the form, but these two things compensate each other. So you can make choices here in the decomposition such that they readjust the form to be of our liking. So that's basically what one needs to do. So this is problem 1 in the problem set 10. Okay, so assuming this is true, now we have our T action which is fixed. We have our 2 form which is fixed. The question is, what's the moment map? So we have coordinates zi. Maybe here we have coordinates x1, xl. So the moment map will be a function of x's and z's. And now the question is what it is. So I think basically now you can probably give me the answer. We computed moment maps for such actions on tori with exactly these symplectic structures many a time. So what will it be? So this should be an element in C star, right? Which is, as usual, R to the K. Maybe like first test question, will it depend actually on those x's? No, right? Because there is no T action, there is no nothing, right? It's this V naught is just a spectator. Now, what happens here? So you have an action on each of those VI's, which will hopefully have a moment map. Then you have a product of VI's. This means you have to add the moment maps, right? So we need to know what's the moment map for one VI. So what is it? Remember, typically there is some whatever ZI squared, right? Or 1/2 ZI squared. So let's say 1/2 ZI squared. And then you need to multiply it by some vector in RK. What's the vector? So there is not that many vectors written. So which one? Yeah, the weight, of course. And since we have many copies, so that's what it is. Now, one small remark. Remember, in principle, we can add a constant if we want. Here, I don't add any constant for a moment, but in principle, I can add any element of T star, and I would get a valid moment map. Now, remember that what we were doing. So we took this point M, and we look at some neighborhood U of M, and we model it on the neighborhood V of the origin inside TMM. So we know that everything is the same under this upgraded Darboux symplectomorphism. So symplectic forms map to each other, actions map to each other. Moment maps don't necessarily map to each other because they are not unique, right? So what happens? So from here we have the moment map mu mapping us to T star. From here we have a moment map mu v. And the question is it true that mu composed with phi equal to mu v? So what do you think? Or should we add some constant? And if yes, which constant?
You just compute the difference.
Right. And the easiest thing to compute the difference is to look at the point M and at the point 0. At the point 0, this guy is just equal to 0, right? Because all the coordinates are equal to 0, so it's just 0. Here, we just don't know what it is. Let's say mu of M. So that's what we have. Now we have a complete local model near a fixed point. So let's discuss a little bit how the image locally looks like. So what does it mean? What does it mean locally? Let me perhaps introduce the following notation. Let me denote by Cm. Yeah, I will upgrade this notation later on. So let me denote by Cm. All positive linear combinations of the weights. So this is a convex cone in T star, right? So what it means geometrically, I have my weights, and I consider all the positive linear combinations. So for instance, here this will be such a cone. Of course, it may also happen that my weights, they have, for instance, this configuration, right? So then the corresponding convex cone will be just the full space. Right? So these are two options. So the claim, which is more or less obvious. So let's take the image mu of the neighborhood of the point M. So this was this neighborhood U. So this will be the following set. I take the set mu of M plus Cm, and I intersect it with some open neighborhood of mu of M. So see, maybe one more picture. I'm not sure, maybe like if I start drawing many pictures, maybe it's a bad sign, means my presentation becomes less formal and less kind of safe. Right, so we want to know what's the image of this guy. And here we have this T star. So that's mu of M. And what does it mean, mu of M plus Cm? So I just translate the cone Cm, which starts at the origin, to the point mu of M. Right? So here is sitting my polyhedral convex cone. And what I'm doing, I'm intersecting the tip of this cone with some open neighborhood. So this is the neighborhood of mu of M. So I'm intersecting it with W. So I'm saying that U maps to this piece of the cone. And in particular, M maps to the tip. Right? So locally, that's how it looks like. So the weights define for you a polyhedral cone. So this cone, as I say, it may be just the whole space, or it may be some small portion of your space, or whatever it is, depending on your weights. Now you take your point M, you translate it to, you send it to mu of M, and you put your cone here. And then just the neighborhood of this point mu of M intersecting with the cone, that's the image of this guy, right? So that's basically the conclusion of our calculation. You see, it already looks quite encouraging, right? Because in the beginning it was not clear at all why polytopes at all, right? But here we see that at least locally it does look like a piece of a polytope. At least if this is if this was a fixed point. Now let me spend the rest of this this hour discussing what happens if this is not a fixed point, but perhaps let me do just one more calculation with fixed points. So right, let me rewrite this formula in the following way. So I'm writing mu phi, and I would like now to pair it with some element psi in T. Right? So what will it give? So this will be mu of m psi plus 1/2 sum from 1 to capital N zi square, and here I will take pairings of those weights with psi. So basically, I would like to project my moment map to some axis. I am choosing one particular straight line, and I would like to project all these to that straight line. In particular, I am interested if by any chance the point M is a local minimum or a local maximum of this function, right? So this function is just a scalar function now. So M is a local minimum of, in fact, we can say mu psi. If, well, I need to impose some condition on those weights, on those pairings between Ni and psi, right? So what's the condition? These coefficients are all non-negative, right? So if and only if all Ni xi is greater or equal than 0, right? So this is just, so our function is just a quadratic polynomial, and the coefficients should be non-negative, right? Then it's going to be a local minimum. And in a similar fashion, it will be a local maximum of mu psi if Ni xi is smaller or equal than 0. Maybe one thing to advertise for the next time. It will turn out that local maxima or minima are in fact global maxima or minima. So that's what we're going to see next time. So that's why those kind of local pictures, they will be of great interest later on. Okay. So much about fixed points. Now I'll tell you something about points which are not necessarily fixed points. And there, so I'm inviting you to catch me with a little bit of cheating. Okay, so the general case. Well, so we have M and M, and we have a stabilizer subgroup, which is in principle smaller than T. So we have its Lie algebra, which injects into the Lie algebra of T. And as a dual map, let me denote it by pi. We have a projection from T star to Tm star. So we're looking at our Hamiltonian T space. And now, so here we've chosen a point M. And I would like to think about it as about a Hamiltonian Tm space. All right?
I'm a bit confused. Is M arbitrary there, or is it a fixed point?
So here, M is a fixed point.
Okay.
Yeah.
Where is that?
No, let's say M. For a moment, let's say M is a fixed point. So let's just say, assuming M is a fixed point, then this is true. Yeah, later on we'll talk more about it. So now M is an arbitrary point. Okay, so this is a Hamiltonian Tm space. So what's the moment map for this Tm action? So mu Tm. So can we produce from this data a moment map for the Tm action? So it should preferably take values in Tm star. So what could it possibly be? So you have a map to T star. You have a natural map from T star to Tm star. No. Right. So so it's a moment map for Tm action. So that's basically the same type of arguments that we've already seen several times. So go check it. This projection composed with a moment map gives you the moment map for the Tm action. Right. So, okay. In particular, for this guy mu Tm, we do have a similar picture, right? So now just the whole discussion we had before applies, right? So mu Tm in terms of coordinates x and z will be mu Tm of m plus some 1/2, sum from 1 to n, and here zi squared times ni's, where ni's are weights of the Tm. Weights of the Tm action. Right. So just the whole discussion we had before is valid because M is a fixed point for Tm, right? So now, now we can just reuse the arguments that we had before. Also, what we see that the image that mu Tm of u, where u is a neighborhood of M, right? So this will be mu Tm of M plus, let me call it Cm Tm intersection with WTM. So this will be a neighborhood of UTM of M. So just the whole discussion we had before is valid. There is a little bit of a problem with the fact that now we are only controlling this projection of the moment map, right? The question is what happens with the rest. We actually want the image of mu, not the image of this pi mu. So, right, so this is a projection. We have a map to some big space, and from there we have a projection on some smaller dimensional space. And we see the shadow on the smaller dimensional space. Let me give you, maybe let's first try to guess the answer, and then I will give you a hand-wavy argument supporting it. And then we discuss what would really need to do if one wanted to prove it. So we have M. So we have a map mu to T star. Here there is a projection to Tm star. So here inside is sitting U, and inside U is sitting M. So we want to know what is mu of U, and this guy we actually know. So here is sitting this pi mu of M plus this Cm Tm intersection with W. Right. So here this looks like a tip of the cone. Now, what do you think this guy looks like? So here we have a full control of the situation, right? Or more or less a full control. We have a tip of the cone, so the point M maps exactly to the tip. What could possibly be this guy? So let's try to guess the answer. All right. So if it's difficult to guess the answer, let me give you a suggestive argument. Right. Suppose I do the following. So I have this Tm as a subspace of T, right? So Tm is a subspace of T. So let's find a rational complement to Tm. So T will now be a direct sum of Tm plus S. Because it's rational, it will integrate to a closed subgroup of T, which is again a torus. So exponential of S is a subtorus in T. Well, now again you can play the same game, right? So there will be S injected into T, and there will be some other projection pi star, T star to S star. Right? Now the question is how does the corresponding moment map? So there will be mu star given to pi star composed with mu, mapping M to S star. So how does this moment map look like on the neighborhood of M? Well, so let me perhaps, if I want to write, yeah, maybe let me state it in the following way. So for size in S, we know that our M is only fixed under the action of Tm. So it's not fixed under the action of S. In fact, there is no subgroup of S, no Lie subgroup of X which would fix it. So this means that if we take psi and S, then the corresponding vector field, the fundamental vector field, will be non-zero. So so S injects into the tangent space at M. And as a consequence, the corresponding differential of the moment map, so this is injective. So then the differential of the moment map at that point will be surjective. So you get everything here. Now, so you have a map with the differential being surjective. How would the image locally look like? You take some small neighborhood of, so you have two manifolds, you map one to the other. The differential at that point is surjective. So you take a small neighborhood here, you map it there. What is going to be? Again, you have two manifolds, right? You at some point the differential of a map from one of them to the other is surjective. So what happens to a very small ball when you map it there?
Mapped to a very small ball.
Sorry?
Gets mapped to a very small ball.
Yeah, absolutely. Yeah, it's going to be yes, absolutely yes. So right. So now mu is equal to this mu Tm plus mu S. We know that the small neighborhood is mapped by mu Tm to this funny thing, right? To complicated thing. So U is mapped to this whatever bar to this mu Tm of M plus CM intersection with this guy. Now plus, but this guy maps it just to a ball, to some neighborhood of a point. So now how is it going to look like? So let's try to draw some pictures of how the images will look like. So mu of U, what can it be? Well, now it depends how big is Tm and how big is S. Right? For instance, if what we already saw, that was the case that T is equal to Tm. Right? So then we have mu of M, and we have this kind of polyhedral cone, and we are taking a tip here. So that's the image. Now, if C is actually equal to S, so at that point the action is at least locally free. So then what happens? As we discussed, we have mu of M, and around mu of M, we're going to have some small ball, right? So that's how it locally looks like. Now, what's the intermediate case? Suppose that Tm is strictly smaller, so Tm is non-zero, and S is non-zero. So then how it's going to look like? Well, very simple. So here we have a direct sum. So we need to take a direct sum of these two pictures. So for instance, let me try to draw it. So on my picture here, Tm is two-dimensional and S is one-dimensional. So that's mu of m. Now the Tm direction is here. So here I have my polyhedral cone and I have its tip. So that's this guy. So that's the Tm direction. But the S direction is this direction here. And in that direction, I have my open ball. You see, here it is. Here is my open ball in the direction of S. So all in all, that's what I have. I have an intersection, or I have an open ball times this intersection of an open ball with the tip of the cone. Right? In fact, one can make this formulation somewhat easier. So in fact, one can put it in the following way. Mu of u is mu of m plus a polyhedral cone intersection with an open ball. What is this polyhedral cone?
Isn't it just CMTM and then you add just
Certainly, there should be right. So I want to express this guy in terms of CMTM. I need to put something like in this space, and we still have some seconds. Tell me. Yes, one. So do you suggest this? Yeah, I think that's correct. Can we write it in a? But you know, here introducing this S was a kind of compromise. Can we write it without S? Quotient, that's a good word, but now you need to change it. So quotient is this guy, right? And we want the other one, the other way around. Quotient back is, yeah. So it's just a preimage or pullback of Cm under this pi. Because what did we add? We add basically all those S directions, right? So we just added everything which was in the preimage of pi. So that's that's the final status at the moment. Here, as I say, it was a little bit of a sketch and a little bit of cheating, but so the local normal form around any point. So you take a neighborhood of any point in your Hamiltonian T space, you map it to T star, and what you get is mu of m plus some polyhedral cone. So this polyhedral cone may have some kind of flat directions. So what? So it's a convex polyhedral cone. Convex combinations of some number of vectors. It might be like wedges like that, or corners, or like the full spaces, or anything. So next time, we'll need to show that from those. So today we completely did, with some gaps, we completely did local models. Now we know how they look, how it locally looks like. So next time, in 2 weeks, our task is to assemble those local models into a global picture. Right now we know how it locally looks like. Maybe just the last test question. So maybe one may have an impression that we already proved the convexity, or that we already proved the theorem. So why this is not the case?
Well, I mean, you could patch together local models situated representation.
Exactly. The bad thing that may happen, for instance, you have your beautiful local model, right? But then somewhere, so this is m, but then somewhere mu of m, but then somewhere very far in your manifold there is another point m prime. So here there is mu of m prime, and its local model is something like this, for instance. So why not? So this certainly would be a very unpleasant surprise, right? So this of course, this should not happen. This doesn't happen, but we need to prove it. So that's what we do in 2 weeks from now.